Today, I'm at the University of Birmingham to show you how to measure the resistivity in a wire. That's the intrinsic property of every material that tells us how easily electric current flows through it. I've always thought that the best way to picture current is to think of water flowing through a river. The properties of the river, its size, its length, and the amount of rocks and fish in it determine how long it takes for a drop of water to travel from one end to the other. It is much easier for current to flow through an object of low resistivity, like this metal ball, than it is to flow through an object of high resistivity, like this rubber ball. This property is related to electrical resistance, but unlike resistivity, resistance is not constant for every material. For a wire, it's dependent on its length. A longer wire has higher resistance because it's more difficult for current to flow through it. This means that resistance is directly proportional to the length of the wire. It is also dependent on the cross-sectional area of the wire, with a smaller area having a higher resistance. This means that resistance is inversely proportional to the area. Finally, resistivity fits in as the constant that links all of these things together, and this is Pouet's law. So, in order to measure the resistivity in a wire, we need to know three things: the length, its cross-sectional area, and the resistance. To obtain the area of the wire, we need to know its diameter, and we're going to measure this with a micrometer. For precision, we'll take the average of 3 measurements. The length of my wire is 10 centimeters. A power supply is used to generate the current, which an ammeter is used to measure. The voltmeter measures the voltage across the wire. Recall that resistance equals voltage divided by current. This means we get a resistance of 0.015 ohms. Going back to Pouet's law, we get a resistivity of 3.83 times 10 to the minus 8 ohm meters. If we halve the length of the wire, we expect the resistivity to also halve. And we see that this is the case. The inverse of resistivity is conductivity. So rubber has a low conductivity and metal has a high conductivity. So it shouldn't be difficult to picture that resistance and hence resistivity increases with increasing temperature, since the more the molecules vibrate, the harder it is for current to flow through. Superconductors are a special type of material that have zero resistivity when cooled below a characteristic temperature. Superconductors are also a key part of research here at the University of Birmingham, with many uses from particle accelerators at the Large Hadron Collider, floating magnetic trains in Japan, and more commonly in MRI scanners in hospitals.